So, welcome back. We just started the topic hydraulic jump at the end of our last lecture. So, we are going to continue with that. Hydraulic jump. Hydraulic jump is a type of rapidly varied flow, and for rapidly varied flow the definition is dy by dx is approximately equal to 1. This means that the rate of change of depth with the streamwise direction is not very small. Okay. So, the flow depth changes occur over relatively short distance, that is the meaning of dy by dx approximately equal to 1. One such example, as I said before, is hydraulic jump. So, these changes in depth can be regarded as discontinuity in free surface elevation. So, dy by dx can go to infinity as well. So, if the depth over a small distance, if it changes rapidly, it can be said that these are sort of a discontinuity in free surface elevation. Okay. So, hydraulic jump results when there is a conflict between the upstream and the downstream influences that control particular section of the channel. So, there is a conflict between the upstream and the downstream influences. So, suppose this is a channel, the flow is coming like this, and there is some influence here, because of which there is a discontinuity, for example, in the free surface, and because the water depth changes very rapidly, this is called hydraulic jump. This hydraulic jump can occur due to many reasons. One of them is sudden elevation bump that can occur, or due to several other phenomena that we are going to see in this lecture. So, one of the examples is a sluice gate. So, sluice gate is a gate like this. This requires that the supercritical flow at the upstream portion downstream portion. So, sluice gate requires supercritical flow at the upstream portion of the channel, whereas the obstruction requires the flow to be subcritical. Okay. Though this phenomenon called hydraulic jump provides the mechanism to make this transition between the two type of flows. Okay. So, one of the most simple hydraulic jump occurs in a horizontal rectangular channel as below. We are going to see the one of the simplest occurrence of hydraulic jump. So, this figure has been taken from Monson, Okishi and Young's book Fluid Mechanics. Okay. So, if there is a flow that is coming like this in this direction, and the water surface elevation due to the influence arises like this, okay, then this is the simplest most case of hydraulic jump. This we are going to derive the equation for hydraulic jump, and we will take the help of this particular figure. So, the flow within the jump. So, what is the area within, what is this within the jump? So, this is the jump, this is the jump area. Okay. So, the flow within the jump is complex, but it is reasonable to assume that flow at section 1 and 2 are nearly uniform, steady and 1D. So, one of the approximations is, however, this is a jump and this area, this flow is quite complex in nature, but we can assume at sections 1 and 2. So, this is 1 and 2, and the control surface that we have assumed starts at section 1 and goes like this and finishes at section 2. So, this is the control surface that we have taken. All right. So, at section 1 and 2, we are taking the flow to be nearly uniform, steady and one dimensional in nature. We have to neglect any wall shear stress within relatively short segment between the section. So, we neglect the wall shear stress tau w for the derivation of the hydraulic jump. Since at section 1 the flow is nearly uniform, steady and 1D, the pressure forces at either section will be hydrostatic. This is another assumption. This is one assumption, and this is the first assumption is that at sections 1 and 2 the flow is considered to be uniform, steady and one dimensional. Second is we have to neglect any wall shear stress within relatively short segment between the sections. The third assumption is that the pressure force at either section is hydrostatic. All right. So, we have seen what the control volume is. So, the x component of momentum equation for control volume is written as, so F1 minus F2, the difference in the hydrostatic pressure can be written as rho q V2 minus V1. So, we go back to our original diagram and see what exactly we are talking. I will take away this ink. So, this pressure F1 and this is also hydrostatic due to hydrostatic pressure. Okay. So, this F1 minus F2 is this F1 minus F2 will be rho q. So, rho q flow rate into V2 minus V1. How do we, you remember, where did we get this equation from? Reynolds transport theorem or momentum equation that we derived in week 2. All right. So, now, so rho q. So, q can be written as A1 V1 is equal to A2 V2. So, A1 V1 is V1 Y1 into B, where B is the width, okay, multiplied, and V2 minus V1 is the change in the velocities, I mean the difference of the velocities between section 2 and 1. All right. So, instead of, so we can actually use this equation here. Now, we need to determine F1 and F2. So, how to determine F1 F2? This is a simplified diagram of the hydrostatic pressure that we have drawn, the force due to the hydrostatic pressure. If you remember, where F1 can be given as rho C1 pressure at the midpoint into A1. So, this will be gamma Y1 by 2 into Y1 B. All right. You see here, half base into height. So, F1 will be gamma Y1 square B by 2. Similarly, because pressure at C1 is gamma Y1 by 2. All right. Similarly, F2 is going to be pressure at C2, is 1 and 2 denote the section. In the control volume. All right. where PC2 is gamma into Y2 by 2, all right. Here B is the channel width as I told you before. All right. So, this equation, momentum equation, therefore, can be written as so you see. So, if you let us try substituting it here and this one here. So, this will be gamma y1 square b by 2 minus gamma y2 square b by 2 is equal to rho v1 y1 b into v2 minus v1. So, b will cancel from both side, okay. And this gamma can come down. So, it will become, this gamma can come down here, all right. So, rho by gamma is going to be g, all right. So, using this we have simply written y1 square minus y2 square is equal to v1 y1 by g into v2 minus v1. So, this is one equation that we get, all right. So, if we use the conservation of mass, that is the continuity equation, it will give us y1 b1 v1 a1 v1, right. So, a1 v1 and this is a2, this we have already actually written before it also, all right, is q. And the energy conservation. So, we have applied momentum conservation, we have applied continuity, now we will write energy conservation. So, between point 1 and 2, y1 plus v1 square by 2g is equal to y2 plus v2 square by 2g plus HL. This is the energy loss, because in the rapidly varied flow there is going to be some energy loss because of the transition from one flow regime to the other, or because you see it is a very complex process. So, we assume there is going to be an energy loss, all right. So, as I told, HL is the head loss. So, we have one equation, two equation and three equation. The matter is we have to solve this, so that we are going to get some some definitive results for y2 and y1. So, it is, we know that head loss is due to violent turbulent mixing and dissipation that occur during the jump. As I said, the phenomenon of the hydraulic jump is quite complex. It's a phenomenon where violent turbulent mixing, so vigorous turbulent mixing is there, and because of that dissipation of heat, I mean dissipation in terms of heat will occur. So, energy is going to be lost during this jump. For the equations written behind, one of the obvious solution is y1 is equal to y2, but this implies that there is not going to be head loss, therefore, implying that there is no jump. So, this is not an acceptable solution to us, because we are assuming that there is going to be a jump. So, one of the solution is y1 is equal to y2, which we neglect. In a second case, another solution is, if we combine equation 19 and 20 to eliminate V2, you go back and see what equation 19 and 20 is, we can eliminate V2 and write everything in terms of V1. So, using these two equation, we can write, see this is equation number 19, 19. So, y1 square minus y2 square by 2 is the same as left hand side. V1 y1 by g is equal to, so here you remember there was a V2 term, this one, this term. So, using the continuity equation that y1 V1 is equal to y2 V2, all right. So, we have written V2 is equal to y1 V1 by y2. Okay. So, instead of V2 we have used the equation number 20 here, and this will become, so we can take one V1 outside as well and y2 also. So, I will just, so how to go from here to here, I will just solve it out. Y1 sorry V1 y1 V1 y1 by g, and let us take from this side V1 outside. Okay, this becomes y1 by y2 minus 1, and this is equal to, now try to multiply up and down both by y2. So, we multiply y2 both side. So, this becomes, so we still V1 y1 by g. So, this becomes V1 square. Now, y1 by y2 into y2 by no, okay, we do not multiply. So, this one is okay, V1 square y1 by g by y1 by y2 minus 1, this we have, okay. So, we take y2 outside. So, V1 square y1 by g and we take y2 outside. So, this is y1 minus this becomes y2, and this is same as this equation. All right. So, this equation you see can be rewritten as y2 by y1 whole square plus y2 by y1 minus 2 Froude number 1 whole square is equal to 0. All right. You see, because Froude number 1 is V by under root g y1 V1. So, Froude number 1 whole square is V1 square by g y1. So, we try to put V1 square by g y1 in this equation. So, if we multiply y1 here, it becomes y1 square. So, this can be written as, this part can be v1 square by g y1 into y1 square by y2 into y2 minus y1. So, this is Froude number 1 whole square. All right. And when this goes inside, this becomes 1 y1 by y2, and let's, and yeah, so this y2 whole square when multiplied here will also be divided here. So, this will become y1 by y2 whole square, and this becomes minus 1 by 2 is equal to Froude number whole square y1 by y2 whole square into 1 minus y1 minus y2. and this on rearranging will come out to give this equation. Okay. So, this is a simple equation which using the only the momentum continuity can be derived. All right. So, now you see this is a quadratic equation in y2 by y1, and Fr1 here is the upstream Froude number. So, there is a question which says obtain equation 21c from equation 21b. All right. So, very simple, I have showed you most of the steps before here in this lecture. How to do that? You have to just do some rearrangement. So, you try this at home and we can discuss that. So, this is a quadratic equation and this will give us a result y2 by y1 is equal to half minus 1 plus minus under root 1 plus 8 Fr1 whole square. Okay. So, this is the solution of the equation. So, we neglect the solution with the minus sign. Okay. Okay, let me just So, we neglect the minus sign, therefore, we get final solution as y2 by y1 is equal to half minus 1. See, because negative solution is neglected because this will give a negative value of y2, okay, which is not possible. All right. So, that minus sign is neglected. So, this is the final solution, and using energy equation, after we have got y2 by y1, we can obtain the head loss HL. All right. And this is completely, so if we are able to find y2 by y1 from this equation, okay, see what happens is when the condition at upstream is always known, we would most of the time know what the discharge is, what the velocity is, what the height of the water is at the upstream end. We would want to find out the situation after the hydraulic jump has occurred. So, in most of the cases y2 and v2 and those things are unknown. So, y1 is known, using this formula we can also find y2 or y2 by y1. So, this is known, Froude number at 1. So, if we know everything at section 1, so Froude number at 1 is also known. We have already find y2 and y1. So, head loss can be calculated using this formula, and this formula has been derived by putting values in energy equation. Okay. Simple. So, I think these two formulas are very important to remember. So, I would suggest you to remember these formulas, because they would prove very helpful in the questions about the hydraulic jump. So, this is a graph that has been drawn. So, this is a graph showing y2 by y1 against the Froude number at 1. All right. So, if you keep plotting, this is HL by y1. All right. This is an area where there cannot be any possible jump, this area. All right. And if you note this particular one, when there is no possible jump when Froude number is less than 1. So, that means at upstream flow must be supercritical. Okay? All right. So, head loss cannot be negative since it violates the law of thermodynamics. We go back to this equation, all right. So, this head loss, it cannot be below this because it violates the law of thermodynamics, all right. So, this means y2 by y1 also cannot be less than 1. And therefore, the Froude number upstream Fr1 is always greater than 1 for hydraulic jump to occur. So, important message that you must remember is that Froude number at section 1 will always be greater than 1 if hydraulic jump is supposed to occur. So, if the Froude number is less than 1 upstream, there cannot be, there is no way hydraulic jump will ever occur. Okay. Therefore, the flow must be supercritical to produce discontinuity called a hydraulic jump, a very important conclusion. Okay. So, these are the classification. So, if Froude number is less than 1, y2 by y1 is equal to 1, jump is impossible. Now, these are, I mean, you should not worry about this much, you know, but at the undergraduate level, but here for your information, if the Froude number at upstream is 1 to 1.7, the standing wave or undulant jump. If it is between 1.7 to 2.5, it is called a weak jump. So, as you know, Froude number at upstream keeps on increasing, the jump becomes more violent and violent. That is an important message that you must remember. So, you do not need to worry about what is the value of Froude number for oscillating jump or what is the Froude number for, you know, balanced steady jump. Main thing is for Froude number less than 1, there is no jump possible, and secondly, if the Froude number at upstream section keeps on increasing, there the jump is going to become more and more violent. Other than that, two formulas, y2 by y1, the depths y2 and y1 in terms of Froude number at location 1 is important, and also the head loss. But head loss you can always, if you know y1 and y2, you can always use the energy equation to find out the head loss. All right. So, this is some example of hydraulic jump, you know. So, there is a constriction, and when it, you know, falls down. So, when S naught is greater than S naught C, and this the water depth increases, and so basically when there is change in slope with respect to critical slope. So, this means when the slope of the bottom was greater than the critical slope and it transits to a region where the slope becomes less than the critical slope, then the hydraulic jump will occur. So, as I said, this is a jump which is caused by change in the channel slope. So, this is the submerged hydraulic jump that can just occur downstream of a sluice gate. So, in this, depending also on the flow conditions, you know, I mean, if many things will depend upon the velocity and other things, but this can occur just downstream of a sluice gate. Okay, here. all right. So, there is one question: in a flow through a rectangular channel for a certain discharge, the Froude number corresponding to two alternative depths are F1 and F2. We have to show that F2 by F1 raised to the power 2 by 3 is equal to 2 plus F2 whole square plus divided by 2 plus F1 whole square. What do you think? This is a question related to the hydraulic jump, yes or no? No. So, this is a question related to alternate depths. So, basically specific energy principle. Okay. So, I will quickly solve this one. Screen. So, let y1 and y2 be the alternative depths. Okay. So, you remember this alternative depths was a concept that was given in specific energy, and specific energy in that cases should be equal, right, at section 2 and section 1. So, let us write E1 or E1 is equal to E2, right, or same thing. So, y1 plus v1 square by 2g is equal to y2 plus v2 square by 2g. So, we will take y1 common. So, it will become 1 plus v1 square by 2g, y1 is equal to y2 1 plus v2 square by 2g y2, all right. And we already know v square by g is equal to Froude number, right, whole square. So, this equation y1 1 plus Fr1 by 2 Fr2 by 2. So, basically y1 by y2 can be written as 1 plus, if Froude number we just write F2 square by 2 F1 square by 2. All right, or y1 by y2 is equal to 2 plus F2 whole square, all right. So, F1 and F2 we already know, correct. So, instead of Q, I mean we also know that F1 square is Q square divided by B square G y1 cube, and F2 square is equal to same thing, Q square divided by B square G y2 cube. Just instead of V we are writing in terms of Q, okay, and B is the channel width. So, using this one we can if we use these two equations here, and we can write f2 square by f1 square using these two here will be equal to y1 cube by y2 cube, right, or y1 by y2 is equal to f2 whole square divided by f1 whole square to the power 1 by 3. All right. Correct. So, this was cube. Yeah. All right. So, y1 by y2 is equal to f2 by f1 to the power 2 by 3 is equal to 2 by f2 square and this was what we had to prove. All right. So, this was the thing that we had to prove. So, basically we started with equating specific energy. So, that was step 1, and step 2 was writing the Froude number in terms of Q and obtaining y1 by y2 from here step 2 and obtaining y1 by y2 from step 1, and equating those will give us the required. So, this was the thing that we had to prove. So, this was one very simple, which was not about hydraulic jump. The questions about hydraulic jump we will start doing in the next, starting from the next class. So, I think this is enough for today, and we will start our probably the last lecture on open channel flow next time. Thank you so much. See you in the next class.